Okay, now, so we're going to go back over kind of the same things that you've seen in the crash course video. But I thought I got to earn my pay, plus it's good to hear it from different people. So you have Dr. Shin, I don't remember her last name completely, but she's really pushy, no, not pushy, punchy and entertaining, and I'm dull and plodding. But we learn, we see it a couple times. And this is how I teach it to my college students. So you'll see this kind of strange looking nomenclature or way of writing about things. And you see CE. So CE is a circuit element. And for us, it's going to basically be resistors, but also LEDs. Oh, and of course motors, resistors, LEDs, and motors, which basically behave as resistors. LEDs are a little different. We might use a regular old light bulb as well. Okay, now you see this delta V. And delta V is just the change in the voltage. So as you saw in the first crash course video with the mountain, and then you have the river of current flowing down. So the height of the mountain is a kind of a delta V. And in our case, it would be the delta V of the battery. And what the resistors would represent, circuit elements, would be if I had the mountain, but then I had some plateaus. So number 1, number 2, and number 3. In fact, that's incorrect. Not the plateau. The first one would be here, the different slopes. And the second and the third, and the flat spots were in the wires because we think that there's no voltage change in a wire. Okay, so we have the idea of circuit element and the delta V. So each element has its own change in voltage from one end to the other. And the idea is that if you didn't have a change in voltage, you couldn't have any current flowing. And then the battery has its own delta V. And we generally think of it as if it's a 1-volt battery, then we say it's plus 1 volt here and 0 at this end, at the negative end of the battery. So the little line is the negative and the big line is the positive, like so. So of course, things we need, one thing that's not on this list is we need some kind of power source, which is a battery or a power supply. We'll be using batteries. So we have that, and to make a circuit, we need a continuous conductive path, and we can say that we need at least one, because we're going to see you could have more than one. At least one conductive path, continuous conductive path. So we can follow this blue line all the way around. We start at the positive terminal of the battery, and we return to the other end. Okay, so what this implies then, we have an important current. So I is current, and the units are amps. And of course, V is voltage, and the unit is volts. So all the current that leaves the battery has to come back to the battery. So that's I total. That's an important one we have to keep in mind. And if we know the total resistance, so R is resistance, and that's in ohms. We also use this Greek symbol. So what it says is that if I multiply I total times R total, it equals to V of the battery or power supply, and the delta is implied. And in fact, each one of these circuit elements has their own delta V, and that can be different depending on whether you have a series or a parallel circuit. Okay. So let's move on to the next one. So now it's the same drawing of the circuit, but now we're going to call this a series circuit. And so there is some X. When we say the word series, then we're adding some extra conditions. So now we have only one current path. And the current everywhere and also inside of the circuit elements themselves. Getting a little lag here with my tablet. So it's very easy to see then that I total that leaves the battery is the same that comes back, because of course it's the same everywhere. And then there's this condition here that the voltage drop across each one of these, when you add them together, equals the voltage drop of the battery. And you see that it can't, if it went to 0 here, then there would be no reason for the current to keep going. If I drop, so each voltage drop is a fraction of the total voltage of the battery. So that's pretty straightforward. So now if we change the circuit elements into resistors, we can apply this thing called Ohm's law. And of course named after a dude named Ohm, believe it or not. And what he discovered through experimentation, that the amount of current equals the voltage divided by resistance for anything. So I know the current here then I can figure out what is the voltage. But what we know is that I1, because we have the magic word series, I1 equals I2 equals I3 equals I2 total. So then that means is that, okay, let's see. So we also know, so we'll slow down a minute. I went a little too fast. We have also, by using Ohm's law, we know that I total equals the battery voltage over R total. That's always true. This is, yeah, see, for all circuits, that's always true. The trick is, what is R total? Now, for the series circuit, now we have this. And what we can do is, we can use Ohm's law, and we can rearrange Ohm's law to say V equals IR. So we don't have to have separate labels. That's interesting. Oh, now it's going to do it over and over again, huh? Oh, crash it. Okay, we're back, and I didn't lose anything. Word auto-saved after all. So anyways, I can take Ohm's law, and I can change I equals V over R to V equals I times R. And so here we could be putting in I1, I2, and I3 and I total, but we don't have to, because we know, because it's a series circuit, that they all equal the same thing. So there's no need to put a subscript on I. So we have V1 plus V2 plus V3 equals V battery. And we know that I total times R total is going to be the V battery. And because the I is the same for everybody, we can use the distributive rule of multiplication. And then we can also just cancel them out. And we're left with this. So this is the rule of combination for series resistors. And we're going to do an exercise to verify this. For series. Okay. Save early, saved often. What's next? So the next one is parallel. So what happens for parallel, we always say that the wire has R equals, oops, starting to write out the word equal. R of a wire equals to, come on, equals to 0. So with V equals to IR, there's no change in voltage over the wire. So let's say whatever the voltage of the battery is, that's going to be the same here as here as here. And everybody here is going to be at 0. So that means that we set these all equal to each other. So now we see I total leaves, I total has to come back. So it splits each time. So you have an I1 here, an I2 here, and an I3 there. And it's easier to think about it down here. So I3, then is I2 plus I3, then we add I1 to get I total. So I total equals the sum of the currents of each. So remember, for the series circuit, it was the sum of the voltages. But for the parallel circuit, it's the sum of the currents. So now we take a look at when we use resistors or resistive elements. We have, once again, our Ohm's law. Once again, this expression is always true no matter what. So then we add into it the conditions from parallel circuits. That's a symbol for parallel. There's two conditions. And then we say, okay, so I equals V over R. We don't have to rearrange anything. So we just substitute into I total and I1, I2, and I3, V total over R total, V total over R1. Now we could have put V1 once again, and V2 and V3, but because of the condition here about the voltages, That's not necessary. Just as before, we didn't have to add subscripts to the currents. So everybody has the same V on the top. So once again, using the law of distributive law of multiplication, we can pull out that V total, and then once again we can cancel it. And now we're left with this expression here, which is just a little bit harder to do than the one before. And let's do an example. Let's say we have, ready? So let's say we have V battery equals 10 volts. And we have the 3 resistors. Let's say we have 10. R2 equals 15. And R3 equals 20. So that means then for our total equals 1 over R1 plus 1 over R2 plus 1 over R3. And so that equals 1 over 10 ohms plus 1 over 15 ohms plus 1 over 20 ohms. And so that's going to equal to, looks like it's going to crash again. It's giving me all kinds of lag here. 0.1 is plus, well, that one I'm going to need my calculator, plus 0.05. Come on, just lasts a little while longer. Don't crash on me. And let's get the calculator out. And we got 15, 1 over x. Of course, that is 0.6, no, 0.0, yep. 0.067, and that equals, let's see, that, and then we add 0.1, and then we add 0.05. All right, so then we're left with 2.17 times 10 to the negative 1, and this is ohms to the negative 1. It's one. Remember, we got to do one more. This is equal to 1 over our total. So to get our total, we got to do 1 over that. We got to inverse that, and then our total equals 4.62 ohms. Come on. So you guys should double check that. Now the important thing to notice is that when I put them in series, the total is less than the smallest one. And that's because of multiple current paths, but we'll learn more about that in the exercise. All right, that's it.